In this video, I look at some reasons why you might consider adapting your coding workflow to accommodate alternative development tools. We also look at examples of the adaptations to your code and workflows that might make this happen. Let's start with the premise that, as developers, there's a lot of the usual suspects in our coding workflows. We've mostly figured out how to work around the quirks of our tools, and if faults emerge during testing, we often have a pretty good idea about how to unravel the puzzle. We get feedback on the validity of our code based on the chatter from the compilers, linkers, and syntax checkers that we use in the toolchain. Our code evolves in response to that feedback. Over scores, if not hundreds of build and test cycles, we learn to recognize the portents in the feedback. Hopefully, our workflows are unremarkable. Of course, none of us are surprised at a change in that tool chatter when we introduce new data structures or interface elements. For my part, I usually prefer to pre-check code with a syntax checker. I expect its feedback to be way more verbose than that of a compiler. I expect it to give me warnings about coding practices that are sloppy. For example, variables I've created but never got around to using, truncation of string variables, silly stuff like doing a quality test on floating point numbers. And this gets me to wondering whether other compilers, other toolchains might generate chatter that's rather closer to that of my syntax checker. My workflow includes lots and lots and lots of tests, but why don't we regularly get a second opinion on the tool chatter that so influences our code? How hard might that be? In this video, we'll see some excerpts from adapting coding and workflows to accommodate an alternative. Is setting up that second opinion worth the bother? Well, maybe it is, maybe it's not, but it rather depends on one of the big risks in software development. And that risk, for better or worse, is that the next release of our tools or our hardware attempts to be more perfect. New terms and conditions, or new language rules which our existing code base is no longer consistent with. As an example, after setting up a new computer and installing what I thought was the usual tool, I type the usual keystrokes and I get whacked by an error. Jumping from GCC version 11 to GCC version 15, wow, there are screeds and screeds of pain in that feedback. And I go back and look, and actually some of those were starting to show up in GCC version 14. Confronted by what might be a seriously iterative rewriting of the code to get past this pain, it might be reasonable to ask whether another tool might actually be less pedantic and a way forward. Some context about this video and the things that you're seeing. I do development work in the ESPR whole building numerical simulation suite. It's roughly a million lines of code. It's a mix of newish and legacy Fortran with some newish and legacy C code for graphics and some C++ for report generation. As with other numerical software, the code has been tweaked just about every week for more than 2 decades. Some of it works by way of styles of code that are a bit opaque to a modern eye, and there are pockets of truly ancient code. Now, this is hardly unique to ESPR. There are some really opaque and tenuous corners in many numerical tools. I regularly compile on several different ages of Linux computers, as well as OS X, and occasionally I generate a native Windows executable set. And I run syntax checks on the source code almost as often as I invoke the toolchain. The trouble with syntax checkers is they have little to say about the code bases that stretch across multiple languages. Of course, any tool set is going to need to work across this mix of requirements. Now, from what I can tell, the LLVM project It's been up and running for quite some time. It actually appears to fit that mix of requirements. So, what's it like setting up clang and flang? Adapting to an alternative tool change is not a coffee break task. It involves learning a new set of rituals and quirks. It's an iterative process of tweaking, hitting brick walls, and scouring the web. Here's a visual difference of one of the scripts that controls the compilation of a dozen applications that make up the ESPR suite. The changes include somewhat different directives depending on the choice of compiler. Now, once the new compilers are invoked, you then are likely to be confronted with the following classic tasks. A new compiler is going to be differently sensitive to sloppy code. It noticed a few places where some of the feedback is like a syntax checker. Happens to be quite a trivial fix. Initial compiles are likely not to find some of the intrinsics that you're used to. Initially, I created local bespoke versions that were controlled by if-def statements. Eventually, I found some of the equivalents under a slightly different name. So you should expect to iterate a little bit to find equivalents. In some cases, to deliver the desired functionality, I needed to access some C functions. This comes with the usual baggage of communicating between computing languages. In some cases, the baggage is extreme. Let's take the rather trivial case of establishing the current time and converting it to a date stamp. This should have been a coffee break task. It turned out to be a pedantic nightmare. gfortran provides an intrinsic called ctime. It returns a date stamp, and there's also an intrinsic time function, which returns the number of seconds since the epoch. Flang has no such convenient functions. However, looking around, both clang and gcc had them. It turns out that the second since the epoch is a C-type that depends on the compiler as well as the version of the compiler. And of course, it might be possible to do it much more elegantly than I did, but I ended up with a rat's nest of if-def statements to sort out all of the different variants. How about the feedback during the build process? Well, it's certainly rather different, and actually a lot more suggestive in quite a few ways, and perhaps it's time to go looking around Stack Overflow for some examples of string comparisons. At some point, we get to the point where it compiles. Bravo! So, but just because it compiles doesn't necessarily mean it runs the same. And, well, actually, we've also got to check to see if it compiles across the variants. Does it compile with older versions of compilers? Because some developers are still working on older computers. In the case of ESPR, there are actually 3 different user interfaces. Does it still actually compile and work with these? So, quite a matrix of variants to get through. And once that matrix has been explored, comes a rather important question for a numerical simulation tool. Does it give the same predictions? Thankfully, ESPR has a self-test facility where several hundred tests are run and a range of reports are generated which compare all the different predictions across all the different models. And at first it would seem that there are rather a lot of reports which have differences. However, if we look at the details, we can see that some involve differences at the second or third decimal place. That's not unexpected. And in others, there's a difference in the time where a maximum or minimum of some reported value changed. In the event, there was one test that significantly failed. And, well, that needs some further investigations, but not bad for a port.